All right, I'm going to talk to you about drag force. Hopefully I won't be as boring as Matt's been, so it'll work out for you better. So with drag force, any of you that deploy in the atmosphere, whether you're coming in on the orbiter, the lander, the balloon, any of it, you're going to have drag. And so we have to do something about that because the standard physics equations don't work for you anymore, the ones that you've been learning in school so far, because they assume a constant acceleration. And we got drag. So drag is a fun little thing that's happening in the aerodynamic world, and so that's going to plague you, and so you've got to be able to handle that in these equations. So if you look, Matt actually already drew up a little diagram for you and stuff on page 66 in your book. So what I'm going to do is basically explain it and show you a little example that I did to kind of help you check your mathematical model and make sure you're doing things correctly. And because I'm going to use numbers that aren't real, and you need to use the numbers that are actually from your design, and so you can use them correctly. All right? So when we have something falling through an atmosphere, right, there's these things that are occurring on it. There's these forces, right? One of them is the mass times the gravity, so that's going to pull it down. And we're also assuming that we're falling straight down, right? So this is the velocity. It's pushing, it's going down. And so when we have something going through a fluid, though, we have this drag force that's pushing up. I don't know, what do you call it? F sub d. Oh, I will use Matt's correct terms here so you don't get confused. F sub d, right? So we got this drag force that's pushing against us. So if we do the sum of forces, right, we got this mg, that's the force pulling us down, and then we've got the drag force pushing us up. And so what those do, because we're moving, it's equal to ma. And so now we can start figuring out some things, because what we really need is to solve for that acceleration, right? So we have mg minus fd over the mass of the object. And that's what we're really about, because our acceleration is going to be changing because drag force is going to be changing. The mass of the thing doesn't change, hopefully, unless it's like falling apart, which is a really sucky idea. But you could do it. But so without that, you're going good, right? So it's really this thing that we've got to figure out, this drag force. Well, drag equals 1/2 the density of the fluid that you're in times the velocity that you're going squared times some drag coefficient, C sub d, which you have to look up, and it depends on the shape. It's totally a geometric property. It's nothing else. So you have to look up what the drag coefficient of your vehicle is, your probe, times, it's called the planform area, S, which is what the fluid sees, the surface area, the area that the fluid sees. So like on a sphere, and that's what we commonly use, a sphere, when it's flying through the atmosphere, actually the only thing it sees is a circle, right? And it sees the maximum diameter. So for a sphere, what we would see, the fluid would see, is this. So S for a sphere is pi 4 over d squared. Or pi over 4 d squared. So that's what we use for that. So you've got to look at it from that perspective. It's not the entire surface area. That's not it. It's just the area that the fluid sees. And you've got to make sure you do that correctly, right? So if we plug all that in, right, and Matt's got it down here, blah, 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 somewhere, yeah. So what we end up wanting, right, we want velocity. And if you look back on page, some page in the early parts of this book, what page was that? 60-something? Matt, come up, help me. 60, the first ones with the physics equations on them. The first page in the book of that part section. Matt's not being a good assistant right now, so... But 62. The velocity, what?
62.
62. So he's got that the velocity, actually it's the final velocity on each time step, is equal to the initial velocity plus AT, right? AT. That's a fundamental equation that you know, that the initial velocity, the final velocity, is the initial velocity plus some acceleration times time, right? And if this was a constant, if acceleration was a constant, we'd be done. But we're not. So we got to plug in for acceleration. So what we end up getting is initial velocity plus, and he's got it down here, gravity times time minus rho v squared c sub d s t divided by m, right? 2m, actually 2m because of the 1/2. So that's what we'll end up using. So we need this velocity, and we got to actually do a time step because it's not going to work, because since we don't have constant acceleration, we can't just say over 5,000 seconds the acceleration is the same. It isn't. So you've got to incrementally time step it, is what I mean. So what you have to do is sum delta t, right? And so that's the change in time. And so like Matt has on here, normally 1 second will work, but it really won't work in this environment. So I think you should use 0.1 seconds, right? So 1/10 of a second should be your time stamp that you do this with. And so that's what's going to help you figure out what this thing's doing. So each time you do it, you'll see how it changes, all right? And then you also, because the bigger thing, you want to know the velocity, but you also want to know the distance. And that's the really neat part. And so the distance equation on page 62, is that what you said? 62. I'm probably off the board now, but distance, right? Final distance is the initial distance. Oh crap, help me here. Plus velocity times time. VI times time.
V equals 1/2 AT squared plus VI times time.
1/2 AT squared, right? Is that right? So that's also what we're going to do, because we need to know distance, right? Because what you end up wanting to know more than often is the time. You want to know from whenever you deploy, and deployment is up to you, right? So if you deploy at 55 kilometers, if you deploy from the balloon at its normal height, when would you hit the ground? Because for most of you, hitting the ground is the end of your mission, right? You want to die. That's the going out with a whimper, not with a bang, right? And so this is the point. You want to know that time because that will tell you how much power you need. You'll know how long you need to keep things alive to know how much batteries to do. So that part really helps you out, okay? So let me show you right quick. I don't have to do like Matt and stop the video and restart it. I can do this magic where I erase and still talk to you. So what we want to do is kind of go through this step by step, because this can get confusing. I know you guys have probably never had to do this before, so I want to make sure you understand it. So we got these two equations, this V final equals V initial plus GT minus rho V squared C sub D ST divided by 2M. And then we also have D final equals D initial plus VIT plus 1/2 AT squared, right? So you can use both of these. So we've already got this one in actually the form that we need it in. So we need to actually put this one, because that A term, right, and this V sub I. So what you got to do is put DI plus VIT plus, and then you need to change it to this A, which is, oh crap, I'm going to try to do this without doing it. Well, fudge. mg minus f sub d over m, right? And then t squared. And so then you've got to plug in f sub d, and you'll get all that fun stuff in there. So basically these are the two that you would use. And so you'll use these each time you start working on this thing. So what you need to do is you have to incrementally do this thing, right? So at time equals 0, these things start falling off real quick because there's really nothing happening. Our time equals 0.1. And so that'll help you out a lot. So you'll just keep going through it. And then you've got to reiterate again and again and again. And so that's the really strange thing about this one, is the final velocity you get for the step, one step, is the initial velocity of the next step, okay? And the same for this. The final velocity, final distance you get in the first step is the initial distance in the second step. And so that's how this works. So when you do that, and I created a model, a mathematical model of one example, and so I'll show you what I got when I did it. So if we do all this out, and I'm not going to go through all the steps with you because I want you to learn how to do it. basically what I said was, okay, I'm going to start at 0. And my velocity is going to be 0. So I'm dropping from something. Now, this is not 0 if you shoot out of the muzzle, right? Because Matt already told you about that one. He gave you that boring lecture about muzzle velocity and deorbiting and all that stuff. So that could be some other number. But for me, it's 0 because I'm just saying bombs away and dropping, right? So that's what I'm after. I'm going to put my timestamp, my time increment at 0.1 second, not 0.01. That would be really slow. 0.1 seconds, right? I went and found, I'm going to do a sphere, and so the drag coefficient for a sphere is 0.47. I actually decided that my sphere was going to be 10 centimeters in diameter, about the size of a light switch plate, right? So when I did that, I did pi over 4 d squared, ooh, that's a 4, right? So I got pi over 4 times 0.1 squared, because I want everything in meters, even though I said centimeters, I wrote meters. That's 0.126 meters squared, right? The G of Venus is about 90% of Earth, so it's 0.91 times 9.81 meters per second squared. Whatever G you use in physics is okay. You're going to be close to, I use 9.81, but whatever you guys decide to do. So that was 8.83 meters per second squared, right? And then I said, I don't care about density, so I'm going to call it 3 kilograms per cubic meter, right? We know density changes on Venus as you get further and further down to the surface. So you might want to change it, or you might want to keep it a constant, but vary it, all right? This is going to require you to use Excel or some sort of mathematical model to make this work, because you're not going to want to do this about 60,000 times, because that's what it's going to take to make this actually hit the surface, okay? So, but you could change the density and say, well, what if it's this? What if it's that? And you will find how long it actually takes for things to hit the surface. And so that's kind of neat, okay? And so that was kind of it. So I use those two equations, right? So the VF equals VI plus GT minus rho V squared C sub D ST divided by 2M. And I just followed exactly what was written on here, right? The other one is DF equals DI plus VIT plus 1/2 AT squared, right? And I just solved for V, or plugged in the A stuff that we found from this equation. And so what I get is the following, and I'm giving you a few data points that if you plug in these numbers into your model, you should get. And then from there, you should be able to then change it because you know your model is correct, at least from what I think it's correct. And then you can go forward and change numbers and know that what you're getting is probably in the ballpark, right? So at time equals 0.1 seconds, right? So we just dropped the sphere, right? And it's this 10 centimeter sphere that's flying through the atmosphere. I got that the velocity at that time increment was 0.883 meters per second. And I got that the distance that it just traveled was 0.4415 meters, right? So it's just barely left us. Then I kept on going because you got to continue to iterate, continue to loop the problem. You just can't plug in this next one like I put at 10 seconds what's happening. I can't just plug in 10 for T. That doesn't work, okay? You got to plug in 0.1, then 0.1, then 0.1, then 0.1, and change the numbers throughout. At 10 seconds, what I got was we'd actually hit terminal velocity, which is 9.970123 meters per second. And I got the distance as 88.2785 meters. That's an 8, right? So I kept on going, and I said that time equals 578 seconds. My velocity was still, because we'd already hit terminal, so I can't travel any faster, right? Was 9.970123, and my distance now was 5,500.536 meters. Okay? And you can see, look, we've almost went, what is that, 10 minutes? 578 seconds, almost 10 minutes, right? 57.8 minutes to be exact. But, no, 10 minutes. Fudge, wrong thing. 10 minutes, around 10 minutes. It's a Sunday morning, I'm tired. 10 minutes, and we went basically 5.5 kilometers. If the balloon is at 55 kilometers, and you want to go the whole way, you have already spent 10 minutes and you've only went a little bit of it, only about 10% of it, 5.5. Actually, exactly 10% of it, 5.5. So it's going to take a while, right? And see, what this is going to do this time is going to help you determine how much battery you need. Because batteries, remember we've been telling you this whole time, watts, W-A-T-T, right? Not watt, but watt. The watt of power, right? Well, batteries are in watt hours. So when you find this time, you then know how much wattage you need. You can find out how much battery you need. And so that's what this stuff is really useful for. And plus it will tell you a lot about the physics. So hopefully this has helped you. I don't want it to confuse you, but I guarantee you, every one of you, almost every one of you, is coming into the atmosphere, is flying around in this atmosphere. And because of how crazy thick this atmosphere is, this is going to have to be done. So drag force is very important for you to remember. Okay? So hopefully this will help you. And if not, it's one of Matt's things that has really bored you to death and not helped you at all. So we'll hopefully help you from there. So bye.